Okay. I did not record the very first lecture this yesterday, so I do want to go back and hit a few of the high points that we did mention. The main thing that we talked about yesterday, and we're going to focus on a few more of them today, is we really focused on group 1. Okay? Some of the most important things that I want you to remember about group 1. How many valence electrons does group 1 have? 1. Group 1 has 1 valence electron. Okay? So, group 1 has 1 valence electron. Since it has 1, what does it want to do with that 1? It wants to get rid of it. So the charge, we know it wants to get rid of 1 electron, but when you get rid of it, what's this charge going to be? Positive. Is donating something a good feeling? Yes, it's Christmas time, so when you donate something, that's a positive thing. So when you donate or give it away, it's going to be a positive sign. Now, the other thing that I want to talk about, I showed you the video. Okay, which metal? Was it the one at the top or the one at the bottom that reacted most violently? Bottom. Now, we didn't do francium. They didn't have that, but they did have cesium. And when they dropped cesium in, what happened to that beaker? It exploded. Okay. So, as we go down the group, what happens to its reactivity? It's more and more and more reactive. Okay? Now, let's think about the reasons why. We know that lithium has 3 electrons and cesium has 55 electrons. Which one of these atoms would be larger? The bottom. So we're already kind of getting into a topic we're going to discuss later. So, atomic radius is one of the things we're going to talk about. So what do you think the trend is as we go down the periodic table in terms of size? It gets larger. Okay, that's a trend we're going to talk about later. Obviously, the reason is because it's going to add more orbitals. So let's just look at it real quick. We know that lithium is 2, so it's 2 and then 1, right? Okay, because lithium has 3. Sodium is next, so we have Na. So it's got 11, so it's got 2, and then how many? 8, and then what? 1. Remember, all group 1s have how many valence? 1. So then if I changed it, and then I went to potassium, potassium's got 19. I've got 2, 8, 8, and then 1. So do you see what's occurring here? Okay, it's getting bigger and bigger and bigger. So by the time I got to cesium, we'd have several different orbital sizes. Does that make sense? So why do you think cesium reacts more violently than lithium? It's got more electrons, but let's think about it in this term. Let's just compare lithium to potassium. Let's pretend that this is you right here in the center. Mary, let's pretend this is you because I have a good thing. Are you eating anything right now? What you eating? What do you have to eat today? Okay. All right, let's pretend that this is a chocolate bar. Because you all, let's talk about sour straws. Those you're a sour straw fan. Let's pretend that this is you right here in the middle with your happy face because you're having sour straws. Do you agree that right now there's several things in your way in order for you to protect that sour straw? Okay? There's a lot of things in your way. So right now, there are several things that's going to prevent you to be able to keep a hold of this sour straw, right? Well, let's go back and let's look at lithium. This is you again right here in the center, and you have your sour straw right there. Which atom would be easier to hold on to its sour straw? Why lithium? It's smaller, right? There's less things in the way. So the larger these things get, there's more and more things in the way. So if I wanted to come by and snatch your sour straw away, which one would it be easier for me to take? Really, really close to you or really far away? Really far away. So the bigger these things get, the easier it is to take the electron off. So when you drop that huge cesium atom into the water, what is that 1 electron going to do? I mean, it's just going to jump off because there's nothing there to protect it. So the larger these things get, the harder it is for the nucleus to maintain its hold on the electron. So, I mean, it's just out there basically by itself, just spinning around with nobody watching it. And so anybody that comes along is just going to snatch that thing right off. Okay, so that's why it reacts so violently. Is that if it gets anywhere near something that can take it, it's going to take it. Okay, that's the reason it works that way. All right, so we talked about group 1, so let's talk about group 2 today and a few of the other groups. Okay, we saw these pictures, saw that. Okay, so let's start right here. The most important thing that I want to talk about, there's 3 important things about this slide. Number 1 is the name. What was the name of group 1? The alkali metals. What is the name of group 2? Alkaline earth. Now, I don't know why it just did that, but I like that much better than it just did that for me. Again, very important. It's the alkaline earth. A little hint, alkaline earth is 2 names, so it's group 2. Okay, so we have beryllium, magnesium, calcium, strontium, barium, and radium. If you look all the way down group 2, those are the elements in that group 2. Now, let's think. I'm moving away from group, so I'm going from group 1 to group 2. Do you think these are more or less reactive? They're actually less reactive. Okay, they're a little less. However, they are still too reactive to actually find them out in nature. You're not just going to go outside and dig up a rock of calcium. You're not going to. It's impossible because it reacts too quickly with the things around it. But there is a way to purify it in order to get some of the calcium out of it, okay? So we can do that. But these bottom 2, along with its name, are the most important. Okay? The bottom 2, along with its name, are the most important. So here's what I want you to do. I want you to add a page below this one for me, please. Okay? And so let's start by drawing this. Alright, so we're just going to do beryllium. What element number is beryllium? It's number 4. Very good. So we've got 4 protons. We've got 4 electrons. How many can the first one hold? 2. Again, a question I asked yesterday, why am I separating the electrons? Negatives repel. Alright, so I've got 4 total. I've used 2. How many do I have left? 1 there, 1 there. Alright, so this goes back to the question I asked you guys yesterday. How many can be held in that second orbital? 8, but it's only got 2. So is it easier to gain 6 or lose 2? All right, so let's do that. So let's draw, and let's say we're going to lose 2 electrons, and now we're going to turn into beryllium with 4 protons, and we're going to turn into beryllium with 2 electrons. So that is what we're going to get. Now, is this normal, regular, old atomic beryllium? No. What has it turned into? Okay, it's turned into an ion. We know it's Be, and if you do your little math here, what do you have more of? You have more protons. How many more? 2. What's the charge of a proton? So that's your charge. It's going to be 2 plus. Okay? It's going to be 2 plus. Now, the last thing I also want to write, which element does it look like now? Very good, it looks like helium. Again, what group do they all want to begin looking like? Noble gases, and that's what's happening. All group 2s, if I did this for magnesium, would it look identical to this? Almost. Would the N be 2 plus, and it would look like a different noble gas? Yeah. But in the end, they're all going to lose 2 electrons. So this answers, if you go back up to the slide right above this after you finish drawing it, and look at those last 2 bullets. Okay? What does the second to last bullet say? Okay? Do you agree that when we did the actual orbital notation, or the orbital diagram, this is a Bohr diagram. The Bohr diagram, there are 2 valence electrons. Okay? What is the last bullet on the slide previous to this say? This charge is, how do you know it's 2 positive? What is it going to do with these 2? It's going to lose them. They're going to get rid of them. Do the pictures help in terms of understanding? Perfect. That's why I draw these pictures. Is sometimes if you just see it, it makes all, because you can memorize group 1 is 1 valence, group 2 is 2 valence, group 1 is 1 plus, group 2 is 2 plus. But if you actually see the Bohr model, it actually concretes the foundation and makes a little bit more sense. Yes, exactly. The Bohr model works in terms of drawing Lewis structures and bonding relationships, but it technically isn't quite right. It's one of those just weird things. It's like, it's so elementary, it helps to use it sometimes. Okay? I do want to point these out. There is some things that I want to make sure you understand is that alkaline earth, is that group 1 or 2? 2 names, it's group 2. They have higher densities and melting points. Now I know I highlighted in that black, but okay. Higher density. What is density again? What's the unit for density? Grams per cubic centimeter. Okay, grams per cubic centimeter. So it has a higher density. Let's look at all the densities. Will they float or sink? They'd all sink. Why? They're greater than 1. Some of the group 1s actually float. If they did not react with water, they would actually float in the water. So it has a higher density and a melting point. Real quick, melting point. What is it going from in melting? Solid to a liquid. What is the melting point, solid to liquid, for water? 0. Look at all of these melting points. Do you agree that they are significantly higher than 0? Yes, significantly higher. Remember yesterday we looked it up for tungsten? Anybody remember? It was 10,000 degrees. No, excuse me, that was boiling point. My bad. Okay. But again, same kind of perspective. All right, and then here, let's talk about this, and this is the last thing. And you'll understand ionization energies later because we're going to get to that topic. But ionization energies are low. Let me state this, and this should make sense. Ionization energy is the energy required to remove an electron. Okay? The energy required to remove an electron. Mary, think about it this way. It would be the energy required for me to walk back there and take your sour straw. Right? You going to battle me for them? Okay. If I take one, would it require more energy or less energy to take the second? Like, I can sneak one away from you, right? That's pretty simple. But what if I come back there for a second one? It's going to get a little bit harder, right? What if I come back there and try for a third one? Not a chance, right? All right, let's say you have 8 sour straws in the pack. What if I come back there and try to get 7 of the 8? Not a chance, right? So do you see how I'm relating this? If there are 7 electrons in an orbital, what are the chances of something taking all 7 when it only needs 1 more? There's not a chance. Okay, we'll kind of get into how that works out. So the ionization energy, again, the energy required to take an electron. They are low, but not as low as alkali, as group 1. Why do you think group 1 has lower ionization energy? Why would it be less energy to take one? They only have one. Okay? They only have that one. What do they want to do with that one? They want to give it away. So it's pretty much almost, it's just almost as simple as possible to take their one. Yes, if you're, and again, I told you this, we're going to talk about how bullies and nerds are acquired, but if you walk up to a nerd and you want their lunch money, does it still require an asking fee? Hey, give that to me. That requires a little bit of amount of energy, okay? All right, these are something to kind of think about. Beryllium does not react with water. Now, what I want you to do, let's go back, and I hate doing this sometimes because it's just such a pain in the butt to do it, but it'll be okay. Because you guys can read it on your own paper as I use it up here. All right, it's the next one right here. All right, what does that first bullet on that slide say that we were just last on? All right, so the top one, let's change colors. This top one does not react with water. Okay, it doesn't at all. Did lithium react with water? Yes. What does the next bullet say? Magnesium. So this one reacts with what? What is steam? It's water vapor. Okay, it's just water that has turned into a gas. What does the next bullet say? The next bullet. So all of these react with water. Okay? All of these react with water. Do me a favor. I need you to write this down below that last little part. Come on. That's H2O, not H2O with a line in it. Let's write those down. X plus 2 H2Os yields X. Be very careful how you write that XOH2 with the parentheses. Yes, it has to be that way. Underneath the very last thing. Yes. No, there's not. It was the pen. Yes, sir. All right, so let me explain something real quick. First and foremost, if I showed you this periodic table, would you find element X anywhere up here? Okay, this X that I'm referring to is any of these metals right here. Calcium, strontium, barium, or radium. Take that X and swap it for any one of these. Now, if you swap X on the left for one of them, what else would you have to do? Put it on the right. So if I plug in calcium for the X here, what would I have to put over here? Calcium. Do you see what I did? I just want to plug in X, and it can represent any of these four. Say it again. Because remember, this one doesn't react, and this one only reacts with steam. Okay, so I just want to work with these four real quick. Does that make sense? Okay. So here's the concept that I want you to understand. Do you agree that these four are metals? Okay. What is H2O? Water. So here's the concept, and I promise you'll learn this in chapter 8 after Christmas. What are we mixing together in terms of the words? A metal and a water. Okay? We're going to get a metal and a water, and here's what we're going to get. Does anybody recognize that OH thing? Say it again. Very good. So what was X again? No. It's a metal. What was OH? So we're putting an X and an OH, so what would this thing be called? A metal hydroxide? Does that make sense? Okay. So we're going to get a metal hydroxide. And then what is H2? Real quick, let me back up for just a second. What are the two blue H's for? Or the two blue 2's? Two blue 2's. That's to balance the equation. Okay, so ignore the blue 2's for just a second. But what is that H2 at the end? No, there's not. Maybe there is. Maybe I don't need that last two. Yep, that looks better. Let's leave that on. Yeah, get rid of that last two. My bad. I did that earlier, wasn't paying any attention to it. Get rid of that. Get rid of the 2 in front of the H2. Thank you very much, Nick. But what is H2? Nope. It's just hydrogen gas. So if I take a piece of calcium metal and I toss it into water, do you think you could see the metal hydroxide being formed or calcium hydroxide being formed? You're not going to see that. But could you see the H2 gas being formed? Let me ask you a question. What is a gas inside of a liquid? It's a bubble. Think about this. When you go swimming and you blow out underneath water, what do you see with your eyes? What is causing the bubble? What is your air? Carbon dioxide. So when you blow carbon dioxide out into water, what do you see? So a gas inside of a liquid is a bubble. What was the 5 signs of a chemical reaction? Bubbles was one of them. Color change, heat and light, rust, and the last one everybody always forgets. A solid precipitant. Okay? So, yeah, you have. A gas. If a gas is formed, is that a sign of a reaction if it bubbles? Yes. This is a chemical reaction. Yes, sir. A what? I mean, it's methane. I mean, it's methane gas. I mean, if you want to call it that, yeah. Okay, so again, but I just wanted you to see the connection that all this does tie together. There are chemical reactions. There are signs of a chemical reaction. There are other things. If you had an indicator, do y'all know what an acid and a base is? Okay, if you had the ability to pour an indicator into this to show the color change, this is going to be a base. Okay, calcium hydroxide or any of the rest of those are going to be bases, and we'll talk about those at a later date as well. Okay. All right. So let's go. Slide 25. All right. I think this is where we go. This is a picture of strontium and calcium. Do you agree that these don't look quite as soft as the other ones that we looked at earlier? Those kind of like nasty old cheese that you could cut. This actually is starting to begin to look like metal. Okay, and it's soft. I mean, you can mash it with your fingers, but it won't react as violently. Yes, sir. The ion is. See, that's one thing whenever you hear about, oh, the fluoride's in toothpaste and the calcium's in your bones. Those things that we're talking about are ions, not solid. It's like iron in your blood. Like, it's an iron ion in the blood. It's not like a solid piece of iron. Now, one of the interesting things that we have talked about is how hydrogen is in group 1, but there's something weird about it. Why does it really not kind of belong with all the other ones we talked about? It's a gas. We call group 1 the alkali metals. Well, here's the issue, but here's why it does belong. Do you agree that hydrogen would be 1s1? Okay, well, let's look at the next one. I do want you to write this down. Lithium. What group number is lithium in? It's in the second, what block? What period? It's in the second period, what block? S, and then which one in the S block? The first one. Well, let's move down. Sodium. What row does sodium start with on? It's 3, what block? S block, what number in there? 1. Well, let's move down. Potassium. Potassium starts at what row? Starts at 4, what letter? And then the first one. So do you see a theme? Does hydrogen's electron configuration match with all the other group 1s? That's why it fits there. So, hydrogen has electron configuration of 1s1, but despite the configuration, it does not share the same properties because, duh, it is a gas. Hydrogen is that unique oddball that can kind of fit into several places. Now, whenever we did this electron configuration, what did we always do with helium? We moved it over. That is the only time that you can do that. But why isn't helium where we put it for that? Why isn't it beside hydrogen at all times? It doesn't have 8, it only has 2. Well, it is a gas, but so is hydrogen. It's noble gas. What does that tell us? It's a stable compound without any need of sharing of electrons. So, like group 2 elements, helium has an NS2 group. Again, if you look at helium, it would be 1s2. And if you go down, helium is that. So if you look at beryllium, beryllium is 2s2, and I could continue on. Magnesium's 3s2. So its electron configuration matches. That's why we have to move it. However, this is the important thing. The highest occupied energy level is filled by 2 electrons, therefore it is stable. So what groups are stable? The noble gases, and that's it. Okay. Remember, the first orbital can only hold 2 electrons. That's exactly why we leave it over there in noble gases. Okay. Real quick, I just want to show you this. I have showed you this before. Period 7. Why does it say 29 to date? There's more that have been discovered since then. I don't know when this was made, and honestly, I don't know how many it is today. But again, that is whenever this was made. That's what they had on there. Okay. I want you to put a big, huge, gigantic star beside this. I want you to look at the picture, and then I'm going to explain the words. If I were to ask you to write numbers in order, do you agree that 1 goes first? and then 2 is second, then 2 again, then 3, then 3, then 4, then 3. Logically, do the numbers make sense? Logically, what should we do with those numbers? They should be swapped. This is what I need you to understand of why 3 comes after 4. This is where the words come into play. Hint, hint, wink, wink. You need to know this. The 3D sub-level is a slightly higher energy than 4S. The reason 3D comes after 4S is because it's a higher energy level. Now, this comes back into Aufbau's principle. How do you feel a roller coaster? So, we're going to talk about this being the front and this back here being the rear. Okay? So, since that's the case, this first up electron would mean we would have how many total if I just saw that one? Do you agree that would be 1 electron and that would just be hydrogen? What if I added a second one? Who would it be? That would be helium. So when we get over here to this, we could fill all the way. When I got to this one right here, the last down arrow, do you remember we go up, 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 down, down, down? Okay, this last down arrow would be argon. Okay, and argon is number 18. What number comes after 18? 19. Well, here's the issue. If I tried to put 3D next, what is the first element number in 3D? It's scandium, which is what number? Can you go from 18 to 21? That's the issue. So the reason you don't go 3P 3D is because there's an energy level that you would skip at the 4S. Now, do you agree that these energy levels are very close? They are, but it's slightly higher. That's why we have to do 3D next. Okay, so this would take care of 19 and 20, and you would take care of potassium and calcium there. But that is why. So again, I want to make sure you know that. This bottom little statement, you should know this already. We've talked about it a lot. The D block is called the transition elements or the transition metals. Okay, that is something that you should have already known. Okay. P block. P block consists of groups 13 through 18. And notice what it says. The P block consists of those except helium. Why is it except helium? Where is helium? It's in the S block. That's why. Okay? Helium actually belongs in the S block. The P block and the S block. Hint, hint, wink, wink, star, star. Listen to what I'm fixing to say. You're going to see this again, I promise. The P block and the S block are known as the main group elements. Hint, hint, wink, wink. The S and the P are known as what? Main group elements. Make sure you know that. So what two did we leave out? The D and the F. Okay? S and P are main group elements. Okay? Now here's something interesting. The properties of the P block vary greatly. So here's what I want to do. I want you to stay on that page, and I'm going to bounce all the way back to the periodic table. Okay? All right, so what I'm going to do is I'm just going to highlight the P block. Now, why did I cross out helium again? It's part of the S. Do you agree inside that yellow square that there are a lot of different colors going on? A lot of different colors. All of those different colors mean the elements are a little bit different. Let's see, we have blue, orange, green, brown, and purple. Is there any other block or group that has that many different colors? There's a lot of things going on the P block. So let's talk about the blue ones to start with. I'm going to circle 3, and I want you to tell me a characteristic about those 3. Al, Sn, and Pb. What are those elements? Very good. Aluminum, tin, and lead. What do we know about those 3? They're all what? They're metals. Okay? Are some metals denser than others? What can you do with aluminum? Can you crush it with your hand? What if I handed you a lead pipe? Good luck. Okay. So again, there are differences within the metals, and we know that obviously. But there are metals in the P block. What are these orange things? They're the things around the stair-step line. We have metals, non-metals, and metalloids. Okay? The orange is the metalloids. In the middle, I think it's the next to last bullet on there. It says something about the metalloids, right? Does it? Okay, all 6 of the metalloids. Out beside that bullet, please write stair, step, line. Out beside that bullet, please write stair, step, line. If you look on the periodic tables on my walls, do you see a red or blue color stair step that goes down to those things? That is the stair step line. The metalloids surround that stair step line. So the way it works is it starts from here. Let me change the size of this pen. Okay, that's our stair step line. And our metalloids are surrounding it. Which element looks like it should be a metalloid, but we obviously know it's not? Aluminum, right? It's touching the line, but we obviously know it's not a metalloid. However, it does have a few characteristics. Does aluminum conduct heat very well? If you put a piece of aluminum foil in the oven for 400 degrees for 20 minutes, can you pull it out with your bare hands? You sure can. Okay. It does not absorb heat very well. Now, it reflects heat, and it traps heat, but it doesn't absorb heat very well. And that's one of its characteristics, tendencies of the other metalloids. Okay. Now, there are some other groups present. What is this purple group? Those are your noble gases. What is this brown group? Those are your halogens. And these other 3 are very important to us. What do we know about nitrogen and oxygen? They're in the atmosphere. What percentage of the atmosphere is nitrogen? You're looking at about 70%. The rest of in oxygen is about, I think, 21%. Without these 2, we would have nothing to breathe. Okay, our body is about 90% water. What is the rest of it made up of? Carbon. Without carbon, you would have no body. Without carbon, you would have no puppy dog. You would have nothing that was living, because all living things are made of carbon. Okay? So, personally, this block is probably the most important, even though it is the most diverse. Very important things that are going on in that particular block. Very important things. Okay, all right, let me get back down to where I was. Let's see, go to slide. I don't know where I was, but we'll find it. I don't think I'm that far yet. Yep, no, that was perfect. Okay. Yeah, the only thing that I want you to write out by the second to last bullet says all 6 of the metalloids are in the P block. I wanted you to write stair-step line beside that, and pretty much everything else is there. Okay. This is important. The oxygen family. Now, I'm going to be honest with you. I have never, ever seen anybody call them the chalcogens or chalchogans. I've never heard that. It's in the textbook, so I put it in there anyways. But there is something that you need to know, and it's this. It's the charge is 2-, and there are 6 valence electrons. And we're fixing to draw that. Now, what do I mean by the oxygen family? That's going from top to bottom. So going from top to bottom. So going down that entire column. So let's prove how we know those 2 facts. So here's what I want you to do. I want you to add a page below that. And I want you to do this. Oxygen has how many electrons, or protons and electrons? 8. Very good. So we've got 8 protons, 8 electrons. How many does the first ring hold? All right. I've got 8 total. How many have I used? How many I have left? 6. So I need to put 6. So I've got 1, 2, 3, 4, 5, needs 6. What's wrong with oxygen? It needs places for 2, right? So, let's go back for the exact same questions I asked you a minute ago. It wants to become full, right? It needs that octet. This goes back to that whole concept. Is it easier to lose 6 or gain 2? Gain 2, very good. So let's make this little drawing. So we're actually going to gain 2. We're actually going to gain 2 electrons. So this time, oxygen is going to go 8 protons to how many electrons? 10 electrons. So we've got an electron here, and I'm just going to write it like this. I'm just going to say 8 electrons. All right, so now, has oxygen turned into an ion? Yes. If you do your little math here, what do you have more of? How many more? 2. What would your sign be? Negative, very good. Here's the way to think about it. Ladies, if you gain 2 pounds, would you be sad? Yes, so is that a bad feeling? So if you gain something, that's a negative thing. Nothing. Some of you may not be sad, I don't know. Some of y'all could gain 2 pounds. Alright, so we know it gained 2, and it doesn't look like oxygen anymore. Who's he looking like now? Looking like neon, very good. Why is it great for him to look like neon? Noble gas, perfect. If I did this for any element in the oxygen family, would they look like this? Yep, it's just going to get bigger and bigger and bigger as I go down. It's always going to have 6 in its outer shell. It's always going to want to gain 2, and it's going to turn into the noble gas right after it. It's going to want to take those 2 in. So, if you go back and look at that bullet that I just showed you, in the Bohr model, I proved both things. Did I prove it had 6 valence electrons? Did I prove that its charge is 2 minus? I proved it using Bohr model. It's, again, you can either learn it as a fact, or you can learn it through a drawing. And sometimes both coincide with each other. Okay? Now, save some space, because we're going to come back to this in just a second. But now let's look at 17. The prefix halo. Kind of put quotes around the word halo. When you think of halo, what do you think about? The game, okay? Like an angel halo. Here's a song. Oh, that stupid song, yeah. All right, well, in science, it's not an angel, it's not a game, it's not a song. Halo means this. Salt producer. If you ever take microbiology in college, one of the things you'll learn about is something called a halophile. What does halo mean? Salt. A halophile is something that loves a salty environment. So where would it live? The ocean. What other places? Stomach. Your stomach? Okay, hold that thought. What about the out there in the desert, the salt basin? Oh, I forgot what it's called. What about the Dead Sea? Why is it called the Dead Sea? It's so much salt, nothing can live in it. Okay? There's other things you'll learn about. You'll learn about halophiles, you'll learn about thermophiles. What do you think they like? Heat. Where would they live? Volcanoes. The last one you'll learn about is acidophiles. What do you think they like? Acid. Where are they going to live? Yeah, or your stomach. Okay. So anywhere there's... What was that, Abby? Huh? Are you burping? Ooh. Alright, so let's look at group 17. Okay? So I want you to draw this. Alright, fluorine. Okay? Fluorine. Fluorine has 9 protons and 9 electrons. I've used 2. How many are left? 1, 2, 3, 4, 5, 6, and 7. So, fluorine has how many available locations? It's got one lonesome little spot. So what do you think it's going to want to do? It's going to want to take one. So it's going to want to gain one electron. So when you do that, fluorine now has 9 protons, 10 electrons. So we've got the first two filled, and I'm just going to circle it now like I did a minute ago. I'm going to write 8 electrons. So we have 8. Now, we know that it turns into an ion. But when you do your little math, how many did it gain? 1. So what would its charge be? -1. Very good. And who does it look like? Looks like neon. All right, do me a favor. I want you to add this. Fluorine is going to become the biggest, baddest bully on the block. So going back, Mary, to our little sour straw thing a minute ago, if you've got 8 sour straws and you're fluorine, am I going to get any of them? Not a chance. Okay? Fluorine does not give up any electrons to anyone but itself. We'll talk about that later. Okay? So the whole point of this that I want you to understand is that how these groups work. This is group 17. Let's think. Group 17 has how many valence electrons? Don't you say 17. It's got 7. Wait a minute. Group 1 had 1. Group 2 had 2. Group 16 had 6. 17 had. So what do you think group 18 has? 8. Okay? So, and if I drew the noble gas, the whole entire full outer ring would have a full octet. So that's how this thing works. Now let's think about something else. Whenever I say the word salt, what's the first thing that comes to your mind? French fries, table salt, which is what chemical formula? NaCl. See, that's the complex that I want to try to break today. When you think of salt, you automatically think sodium chloride. Well, let's talk about the chemistry and let's talk about the actuality. Do you agree that chlorine, 17 protons, 17 electrons, we've got electron here, and then we've got 8 electrons, and then we've got our 7. 1, 2, 3, 4, 5, 6, and 7. So, chlorine has its one empty little space, and sodium So, here, let's actually change this up a little bit. Sorry. So, if I take the chlorine atom with its 7 valence electrons, and I take the sodium atom with its 1 valence electron, what do you think is going to happen? What's chlorine going to do? It's going to take this electron and it's going to make a bond. So when you have that, you have NaCl, sodium chloride. Yes, this works. Yes, this is a salt. But here's the actuality complex I need to break. Is this the only salt? No. Anytime you have a halogen bonded with something, it is a salt. What if I would take sodium and bond it with fluorine? Would it still be a salt? Yes. And here's the mind-blowing thing that a lot of people are like, what? The salt you use on the table is not sodium chloride. What is it? Sodium iodide. Why? When you read the box, it's iodized salt. So it's sodium iodine. That's what you're actually putting on your french fries, not sodium chloride. Yes, there is things called sea salt and all those other things, but most table salt is sodium iodide. Yes, sir. I really don't know what sea salt is, to be quite honest with you. I think it's more like engineered and all kinds. I mean, I really technically don't know the full extent of it. But the whole part that I want you to understand is that it just doesn't have to be just table salt or just the sodium chloride. It is the only salt. Okay? All right, and again, the last thing, group 18, noble gas is non-reactive, charge is 0 because it has 8 valence electrons. All right, I want to point this out as well. Again, we've already talked about this. I do want you to add this for me. Find this real quick. Remember, we know group 17 is the halogens, fluorine, chlorine, bromine, iodine, and astatine. Add this right here. Astatine is radioactive. From now and forever, you'll never ever hear me talk about astatine. So if you hear me talk about the halogens, pretty much ignore that. I'm just talking about the first 4. Fluorine, bromine, chlorine, and iodine. Those are the first 4. The halogens are the most reactive nonmetals. Okay, most reactive nonmetals. Do me a favor and add this. Say group 1. Most reactive metals. Please add that for me. Group 1, most reactive metals. So what do you think group 1 and group 17 do quite often? They react. Why? Group 17 needs what? They need 1. What does group 1 have? That 1. So they trade off and swap. Again, they react vigorously with most metals to form salts, and they have 7 valence electrons with that -1 charge. Okay? The reason why it's -1 is because what? They gain an electron. Okay, that's the reason why it's negative, is it gains an electron. All right, I do want to point this out real quick. All right, everybody, I mean, if you have to look at the other periodic tables, but that was probably the easiest to see. Look in group 17. What is the color of the letters of F and Cl? Red, which tells you that's what state of matter? Gas, very good. Look down. Br is what color? Which means it's what? What is the only other blue up there? Mercury. The only 2 elements, if you were to go out in nature and try to find them in liquid, would be bromine and mercury. Those are the only 2. And then finally, look at I. What color is it? It's black, which means it's what state? Solid. So here's the thing. In one family, we have 2 gases, 1 liquid, and 1 solid. That's one whole family. Why do they change? What makes them different? Why are they not all gases? Why are they not all solids? Why are they not all liquids? Okay, we're going to get into that a little bit later in terms of how the bonding works and how the intermolecular forces of those compounds work. And again, that's what gives them their states. But I do want to show you this chlorine gas. If you were to breathe that in, what would happen? You would definitely die. Okay? It's asphyxiation. I mean, it would choke you to death. It's toxic, and it would choke you. There may be, but I don't know. Okay, bromine. This is a liquid. Now, this does have a very, very low boiling point. It's right above room temperature. What does it mean by boiling point? Don't say boils. I get that. Liquid to a gas. It's a little above room temperature, but it will start to boil at a low temperature. Okay? And then finally, iodine is a solid. But I want you to do this for me. Add this word right here, underneath that. Now, when you think of iodine, how many of you think of that brown stuff at hospitals they rub on you that's just gross? Okay, it's like a yellow color. Yes, it has iodine in it, but no, it is not pure iodine. Pure iodine reacts quite a bit differently. Iodine solid, if you find it in the nature, it actually goes through the process of sublimizing. To sublimize. That is the process. What is sublimation? Perfect. Okay. To sublimize means to go from a solid straight into a gas. So what does that mean? It skips what? Skips the liquid phase. If you were to actually take some iodine and set it out, you would see it start to smoke. Now, smoke is a common word, but really what it's doing is it's sublimizing. It's turning into the vapor. And if you were to inhale those vapors, it's toxic. It would kill you as well. Okay? So again, it's very dangerous to us. It is a purplish color. So that purple haze you see is the vapors. All right, so here's the concept that I want to bring out one last time. Sodium solid. What happens when I put sodium solid with water? Does it react? Okay. What if I have chlorine gas? What would happen? It'll kill you, right? Well, what we do when we put them together, we eat it. Explain that concept. The two natural components, what I mean by natural is what you find in nature, of things we eat, sodium chloride, one would blow up in our stomachs and kill us, and the other one would kill us because it'd choke us to death. Yet, we put them together and we can eat it. What? Sodium, again, that I'm talking about the natural components, and here's the concept. This is not really what we're eating. It does not come from its natural components. What it comes from are those things. And what are those things that are charged? Ions. It doesn't come from the natural stuff. It comes from the ions. Okay, and we'll kind of get into that a little bit later. So it's actually going to come from a compound. And so that's how a lot of this stuff works. All right. Yes. All right, 3 more slides and we're done. 3 more. This one will go real quick. This is the part where I wanted you to say this. Metalloids, again, where are those located? The stair step. Please add that again. I want to make sure that you know where this is. It's the stair step. This little bottom part, yeah, it's important, but you can kind of go through it real quick. Metals of the P block are harder and denser than the S block, but softer and less dense than the D block. Okay, so aluminum, tin, lead, they're harder and more dense than like sodium and potassium and calcium and all that, but they're less dense than copper and nickel and gold and all that other stuff. So that's kind of how that will work when you're comparing the blocks. Now, what do we know about the F block? What do we do with it? Forget about it. There are 3 things I want you to know about the F block in terms of the concepts. Matter of fact, 2 things. The first row, its name is the lanthanides. You will have to know the names. The first row is the lanthanides. The bottom row is the actinides. Let me give you a little hint. Can you see the top row, the F block down there? What is the first box? What are the letters? LA. That's lanthanum. What is the top row called? The lanthanides. That's where it comes from. What is the first box of the bottom row? That's actinium. What's the bottom row called? The actinides. One other little memory trick. Where do we live? Dothan, where do we live? Alabama. What part of Alabama? Lower Alabama. LA. Lower LA. L's above A. Lower Alabama. Okay. Whatever helps. Okay. Last slide. Real quick, and it's kind of a little quiz thing. We're going to end on this. How many electrons the following give or take, and what charge will they take on? All right, so let's talk about this. Calcium. What group? All right, it's in group 2. So it's got how many valence electrons? All right, so 2 valence electrons. So what's its charge going to be? Very good. So 2 plus. You do the other 3, and we'll call it quits. chlorine. What group is chlorine in? It's not group 7. It's in group 17. All right, it's in group 17, so how many valence electrons? 7 valence electrons. So what's its charge going to be? 1 negative. Very good. It wants to gain 1. All right, oxygen, what group? Good. Group 16, so how many valence electrons? 6. And then what's its charge? Negative 2. Very good. And iodine will be the exact same as chlorine. Okay, iodine is the exact same as chlorine. All right, very good, guys. And we'll pick up with, I think, periodic trends tomorrow.